All right, so one more time, just so that we've got it written down up on the screen. What do we call A again? Leading coefficient. And on graph number 3, what can you tell me about the leading coefficient? It's positive. How do we know it's positive? Right side of the graph is going up. We specifically always look at the right side of the graph for our leading coefficient. Yep. So right side is going up. And so A is greater than 0. It's a positive number. This idea right here, this notation, is something that I want you guys to begin to become familiar with. When we're saying something is a positive number, that's the same as saying it's bigger than 0. If I think about a number line, the positive numbers are all bigger than 0 numbers. What about on graph number 4? What can you tell me about our leading coefficient? What can you tell me about A? It's negative because right side is pointing down. So right here, my right side is down. And so we know that A is less than 0. It is a negative number. One of the biggest reasons why I want you guys to become familiar with this notation is on multiple choice questions. It might not say positive number. It might have this notation instead. I want you to know and understand that this means a positive number, that this means a negative number right here. If you're writing an answer out for me and you write this, I'm fine with that. But on a multiple choice, that might not be one of the options. I don't want you to miss what the right answer is just because you're not familiar with the way they've written it. What else did they ask me to talk about? Not just A, but also C. What were we calling C again? What part of the graph is this? That's our y-intercept. So on graph number 3, what can you tell me about the y-intercept? It's negative. It is down here. And so C is less than 0. It's a negative number. What about on graph number 4? What can you tell me about the y-intercept? It's a positive. How do we know that it's positive on graph number 4? How is it positive? Where is our y-intercept? It's right here, which is up above the x-axis where my positive numbers are. So here's my y-intercept. So C is greater than 0. It's a positive number. So far, so good? All right. Let's see if we can answer number 5. Number 5 is a challenge problem. If you felt reasonably comfortable with how to answer number 3 and number 4, you knew whether A was positive or negative, you knew whether C was positive or negative, or if you got it wrong, you understand where you made your mistake and you're confident that you could answer correctly next time, you are right on pace. 5 is a challenge question. If you didn't understand the question, that's okay. I'm going to go through the explanation of it, and we're going to talk through it. And if the explanation at least kind of makes sense in the moment, that's all right. They're asking me if I can determine anything about B based on these graphs. What kind of shape are both of these graphs? What do we call that shape? Parabolas. There was something that we talked about with parabolas in the last unit that had a formula. What was one of the important key features of parabolas? Yes. They had an axis of symmetry. Runs right down through the center of my parabola. I want to look at graph number 3 for just a moment. My axis of symmetry, it's got to go right through my vertex. Would be right here. axis of symmetry is always x equals and then a number, right?
Yeah.
Based on this graph, would the axis of symmetry be x equals a positive number or x equals a negative number?
Negative.
Negative. Because it's going through the negative side on that x-axis. I don't know what the number is. I just know it's a negative number. You guys okay with that? What's the formula for the axis of symmetry? X equals, I heard b over 2a. That's almost correct. There's one other missing piece. Negative up here with my b. That's part of my formula. We said on number 3, so on graph 3, that this whole thing was going to come out to be what kind of number? A negative number. So I have some kind of negative number that would be equal to negative b over 2. What did we say about a on this graph? I don't know that it's 1, but I do know that it's what kind of number. I know it's a positive number because the right side is going up. So if I have 2 times a positive number and this whole fraction comes out to be a negative, because my axis of symmetry is negative, what kind of number would b have to be? A positive, because the negative came from the formula. B would have to be some kind of a positive number. B would have to be a positive number. B is greater than 0. Do you guys follow with how I figured that out? Let's try applying that same idea to graph number 4. When I look at that one, would the axis of symmetry be a positive number or a negative number? Positive. Axis of symmetry, because it's over there on the right side. Would be x equals a positive number. All right, so I'm going to do the same kind of thing that I did with graph number 3. I have a positive number that would be equal to negative b over 2a. But what did we say about a over here? On graph number 4, a was a negative number. How did we know that again? Because the right side is going down. So what kind of number would be on the bottom of my fraction? It's going to be a negative because I'm taking 2 times some negative number. And a negative divided by negative would give me a positive. That's what I said it would come out to be. So what kind of number is b? It would have to be a positive. Otherwise, I'd have a negative and a negative up here. So b has to be a positive number because this negative sign right here is coming from my formula. And then I put the number for b into it. So b would have to be a positive number. If I kind of lost you on the explanation for this one down here, but you understood when we did number 3 and number 4 above, you're okay. Like I said, number 5 was a challenge problem. We're kind of stretching beyond. All right? Let's go ahead and open up your books. We're going to be on page 215 to start for today. Page 215 to start with. So yesterday we talked about power functions. Power functions are special types of polynomial functions. In our power function, how many terms did we have yesterday? We only had one term. Everything was a monomial. In a polynomial function, we can have lots of terms, but only one variable. This is the basic form of a polynomial function. I do not expect you guys to memorize this or even to write it down like this again. But what this is telling me is that right at the very front, this is where I should see the biggest exponent. And then every term after that, the exponent should be decreasing in size until I get to my constant, my y-intercept that has no variables at all. That's all that notation is trying to tell me. This has been written in standard form. Standard form, again, means I start with the highest power at the front, and then it goes down in powers. So my exponents get smaller and smaller and smaller as I go further along in my polynomial. The degree of the polynomial is going to be the same as the biggest exponent. Please go ahead and write this in your book. Degree equals biggest exponent. Write that into your book, please, because your book has a lot of math-ese around there, and I'm trying to just draw out the biggest ideas. Biggest, most important ideas. Our leading coefficient will always be connected to the term that has x with the biggest exponent on it. So wherever we go to look for the degree, I'm going to look right in front of that x for my leading coefficient. How many different variables am I allowed to have again? One. Polynomial in one variable. So they all have to be x's, or they all have to be y's, or they all have to be m's, but it's only allowed to be one variable. If I have two variables, I cannot answer questions about the degree and the leading coefficient, because that is not a polynomial in one variable. Last thing before we actually go and look at some examples. Polynomial functions. We've talked about polynomial functions before, but I've never actually used that word. A constant function, flat line, any kind of function that I can draw without picking up my pencil is a polynomial function. I go from the left side of the graph to the right side of the graph without picking up my pencil. A linear function is another example of a polynomial. A quadratic function, a parabola, that's a polynomial. What do you think we would call a function where the degree is 3? Not a monomial. It's a cubic function. If it's bigger than degree 3, we don't normally refer to them by names like cubic or quadratic. There are names for it. Quartic would be a 4th degree function. Quintic is a 5th degree function. Hexic is a 6th degree function. But we don't normally use those words. Those are not vocabulary terms I expect you guys to know. What I do expect you to know is that the degree tells you the maximum number of times that a polynomial intersects the x-axis. So the degree is equal to the maximum number of x-intercepts. That I do need you to know. Whatever the degree of my polynomial is, that is the maximum number of times that it can cross the x-axis. Do you guys remember our 4 synonyms? There was x-intercepts and what was another one? X-intercepts. We had 4 synonyms. What'd you say? Zeros, roots. There was one more. Solutions. When we call these zeros, my x-intercepts are very specifically real roots or real zeros. In the last unit, we learned about imaginary numbers. A polynomial could have imaginary roots, but when I'm looking at the graph, the x-intercepts are the real roots or the real zeros because it's actually touching my x-axis. So far, so good? All right. We're going to do 2 pretty easy examples, and we're going to do one where it's not necessarily hard, but what we're practicing is how to put things into the calculator. So there's not much that I'm going to expect you to do as far as like super head knowledge here, but we're going to practice typing it into the calculator and making sure that we can get the correct things back. So we'll start with the 2 easy ones. Example number 3 should be right underneath this section where we were talking about polynomials. Example number 3 is still on page 215, just down at the bottom of the page. We want to state the degree and the leading coefficient of each of these polynomials in one variable. If it is not a polynomial in one variable, then we need to explain. We will not give the degree and the leading coefficient if it has more than one variable. So on part A, what's my degree? On example A right here, what is my degree? By the way, I don't know why there's an A there. Let's just scribble that out. Remember, degree is the biggest exponent. What is my biggest exponent? 4. Here's my degree. What is our leading coefficient then? If 4 is the degree, 2. Here's my leading coefficient. So what do you know about this graph? Leading coefficient is 2. It's positive. So what do I know about the graph? Which side goes up? Right side goes up. What's the left side doing? How do you know? Degree is even, so the left side is doing the same thing. Part B. What is my degree? 3. Biggest exponent is my degree. What's our leading coefficient? 7. So what do we know about this polynomial? Right side's going up because we have a positive leading coefficient. What's the left side doing? It's going down. Why is it going down? Odd is opposite on the other side. Perfect. Yes? When you're talking about the ends have to do just with that degree. The leading coefficient tells you whether the right side goes up or down, but it doesn't tell you what the left side does at all. Yes, ma'am. Yes, you may. Part C. Can I find the degree on part C? No. Why not? More than one variable. What are the variables that we have here? We have x and we have y. So I don't have to say the degree or the leading coefficient. I get to skip it if there's more than one variable. It is not a polynomial in one variable, so I move on. What about part D? What is my degree? 5. What's the leading coefficient? 1. There is no number in front of x to the 5th, so my leading coefficient is a 1. 1 is the only number that when I've got it next to a variable is allowed to be invisible. No, you don't have to add it in there. I drew it in there just so we can kind of see it.
No, I mean like the degrees on every
Oh, these other ones back here? Yep. Those are not the degree of my polynomial. We just leave those be. I just want the biggest. I had a really good question in 4th period. They said, I notice on each of these, that's the first piece of these polynomials. Will it always be the first? If it's in standard form, it will. But sometimes they do try to trick you, and they'll mix them up. They won't write it in order down here. You want to find the biggest exponent. That's your degree, and the number in front of that x is your leading coefficient, even if they didn't write it in the front. Does that make sense? All right. So that's our first example for today. Let's go do the other easy example, and then we'll do the one that requires some calculator work. We're going to go to example number 5 for this one, which is actually on page 217. Example number 5. They want me to look at the graph and find out how many real zeros there are. What did we say real zeros were? Give me a synonym. X-intercepts. How many of those am I looking at on this graph? How many times does the graph cross the x-axis? Let's count them. 1 right here. 1 right here. Are there any others? 1 right here. I have 3 x-intercepts. And so that means I have 3 real zeros. So far, so good? Right. These 2 that we've done, that's where your homework focuses, but we're going to go and do example number 4 yet, which is back a page on 216, because we need some practice with plugging numbers into the calculator and making sure that we're getting the right output. That's what we're going to focus on example number 4, okay? So this problem says the density of the sun in grams per centimeter cubed expressed as a percent of the distance from the core of the sun to its surface can be modeled by. Here's where my ears start to perk up because it gives me a function rule now. The function rule is so big that it wraps down around to the next line. That function rule is that whole big long thing there. At the core, x is 0. This would be 0% away from the center. It says at the surface, x is 1. What do you think that represents? Like, what would that be as a percent? 0 is 0%. 1 is not 1%, not 10%. Keep going. 100%. The whole number 1 is the same thing as a 100%. Percent is a compound word, 2 words that we took and smashed together. It means out of 100. So if I do 100 out of 100, that simplifies to 1. They want us to find the density of the sun at a radius of 60%. What is 60% in decimal form? 0.60. 0.60. You take whatever number they gave you. In this case, it was 60%. So I take 60 and I divide it by 100. That's how we get our decimal. That's how you take a percent and convert it into its decimal form. You divide it by 100. Yes, sir. Black pen. Yes, I do. It's brand new, so you might need to scribble it around a little bit to get the ink flowing. All right. Here's where we're going to flex your calculator skills. You guys ready? Everybody has a yellow calculator in front of them. We are going to practice substituting this 0.60 into this polynomial. Everywhere they have an x, so right here, right here, right here, and right here, we're going to substitute in this value. So I'm going to pull up my Desmos calculator on the screen so that we can practice typing it in together, and I'll tell you where any special keys are. All right. So the first thing that we're going to do is just verify that we can get the same numbers. They substituted in one at a time. If you look on your page, they substituted in, and then they have the value that it is right underneath. We're going to make sure that we can get these numbers. All right? So the first thing I need to do is 519. Grab your calculators. 519. And then we're going to make a substitution because then there's an x there, right? Parentheses anytime we make a substitution. So parentheses, what are we putting in for x? 0.60. And then I want you to close your parentheses. What power are we raising it to? Fourth power. How do we get to a fourth power on these yellow calculators? I only know how to do x squared. That would work if we weren't multiplying it by 519. Here's what I want you guys to do. Here's how we do a fourth power. Here's how we do any power that's not just squared. You guys see the x squared button right here by the 7? The button right above it looks like the top part of a triangle, but it's missing the bottom. Do you see that button that looks like a triangle missing the bottom? Push that one. That will let you put in your exponent of 4.
Where?
Do you see the x squared key right by the 7? Right above that one. It looks like the top part of a triangle.
Yeah, I see it.
Yep, right here.
Oh yeah.
Yes, sir.
Oh yeah.
Won't you be able to do this too? Give it, find it this. Replace 2 with 4.
You can, yeah. But to reduce button pushes, you could just do this and then put the 4 in. But yes, you could do that. Do you guys see this number after you hit enter? 67.2624. I'm going to come around and make sure that everybody has this up on their calculator screen. If you see this on your calculator screen, put a little check mark in your book where you see that number. That's it for me, guys. I want you to practice putting this in the calculator. Yep, hit enter. Perfect. So in your book, right here, put a check mark there. Practice putting this into your calculator. Once you get into the calculator, yep, you have the check mark right there. You guys okay getting take a calculator?
Yeah,
All right. Perfect. We'll be on the next page. So right here, where it had that 67.264, the little check mark there. What's the next piece of this polynomial function? What's the next part? We're supposed to substitute in again. So minus 1630, and then we have another substitution. So on your calculator, what we're going to do It was minus, what, 1, 6. What were the other numbers?
30.
1630. And then there's an x. What am I putting in for x? 0.60, just like before. How do I do the cubed? Yep. Find that button that looks like the top part of a triangle and put in cubed. Make sure that you can get this value on your calculator. So far, so good? So that was minus 352.08. Minus 352.08. We're going to do another substitution. What's the next piece? What's the next part of my polynomial? 1844. And then it has x. What are we putting in for x? 0.60. What are we doing to that x? Squaring it. You should get 663.84. Is there any other places where there's an x that we need to substitute in? Was it a plus or a minus? Minus 889. What are we putting in for x? 0.60, just like we've been doing. I got a minus 533.4.
Now, where would just 0.6 as well?
You could just do 0.6, yes. All right, let's put this all together. What was the first number that we had? 67.2624. That was the first number. And then we're going to subtract the second number, so minus 352.08. Minus 352.08. Guys, practice this with me because you're going to do one on your own here in just a minute, all right? And then what? I've got this point. Do I add or subtract this one? Add, so plus 663.84. I've got 1, 2, 3. How many more terms do I have to go? How many terms did my polynomial have? 1, 2, 3. I need this one. Are there any terms after this one?
Mm-hmm.
It didn't have an x with it, but yes, there's one more term. So I'm going to subtract, and then I'm going to add. So minus 533.4. What am I adding? Plus 155. And there's my answer right there. 0.6224. $0.6224. That's what I want down here. All right. I want to get some more practice with this. I'm going to put tables full because we're going to substitute again. We're going to do this as teams, though. Instead of everybody doing all the parts, we're going to do them as teams, okay? So I want you to do exactly what we did here to get that 0.62204. We're going to do it with these values for x. They already gave us some of them. Front table up here, Shadrach, Ian, Emily, Jaden. You guys are going to substitute 0.2 into that polynomial in the place of x. Work together, compare, make sure you get the same answer because I'm going to ask you guys for what that is so that we can fill in over here. Middle table right here, Makai, Elena, Amari, Trent. You guys have 0.3. Eric, David, and my back table. Eric, did you hear me? Cool. You guys have 0.5. So I want you to do that one. Two gentlemen in the back, and this table right here. You guys have 0.8. And you three in the front, you guys have 0.9. Okay? All right. So I want you to practice substituting in. You have to substitute in 4 places. You're going to add 5 terms into this polynomial right here. So whatever your value for x is, you're going to put it in here, 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 and here. I need you guys to substitute in, find it on your own first, then compare with the other people at your table. And then once we've had a chance to compare amongst ourselves, then I'll put the answers up for each of these by asking you guys what it is. Okay? Let's take about 4 minutes to do that, or until everybody's done, whichever comes first. All right? So just like we did here, you want to substitute into each of these, and then you're going to add them all together at the end. All right? I believe that is correct for that first piece. Yeah. That is not the full thing. Yeah. Yep. right, let's see what we got. 0.2 table. What did you guys get? Front table up here, what do we get? 38. When I did that, I got 7504, but you got the 38 part, right? Okay. Let's go look, see if we can figure out where we have a difference. So this would be a 0.2 here. So that should have been 0.8304. Second term should have been minus 1304. Come on. Oh my goodness. Let me get in there. Third term should have been 73.76. And that last term there should have been minus 177.8. Did you find where your mistake was? Very small mistake, yeah. Second one, okay. So for 0.2, you guys should get 38.7504. If that was not your table, go ahead and write it down in that spot. All right. My table that had 0.03, or sorry, 0.3. I just read that wrong. 0.3. What did you get?
14.4539.
Yes, 14.4539. Again, if this was not your table, go ahead and write it down as well. All right. My 0.5, that was my back two tables here. What did you get?
We got 0.1875.
0.1875.
I did that.
Nice work. All right, my group that had 0.8, that was this table here and the two gentlemen in the back. What did we get there? 1.9824. And last but not least, my front table here, 0.9. What'd you get?
Negative 154.
No.
214.
Well, let's look at that one together. Let's go back and check it. So we're going to substitute 0.9 in. So that first term should have been 340.5159. Second term should have been minus 118827. Let's see if it'll let me get in here. No, it's going to keep being a jerk. Third term should have been plus 149364. Next to last term should have been minus 800.1. All right, so did you remember to add the 155 on the end? Because you should have added up 5 terms altogether. So let's add all those up. Let me do it on mine the same time that you check yours. 340, 5159. 340, 5159. Minus 18827. Minus 1188.27 plus 1493.64 minus 800.1 plus 155. There we go. That's probably everything that was making the difference. So you should have gotten 0.7859 for that last one. 0.7859. Do you guys feel reasonably comfortable with substituting in and finding these values? Okay. Yep. If this is a test or a quiz, I'm not going to give you decimals and a super long polynomial. But we are going to practice again tomorrow with substituting into a polynomial and getting a value back out so that we can graph that. Yes, ma'am. They're almost finished. I'm going to pass those back tomorrow, yes. Your homework, due on Friday. Yesterday's lesson, you were able to do the first 5. 1 through 4 went with example number 1 and then that extra example that I provided. Number 5 on the homework was like example 2. From today's lesson, these 3 can be done like we did example 3. So what's your degree? What's your leading coefficient? These right here, there's 6 problems, but all I want to know is the real zeros. How many x-intercepts does it have? All right? And then tomorrow, we're going to do a warm-up. We're going to do one more example. I'm going to make up a problem where we substitute in. The example will be in your book, and then I'll make one up. And then you guys will have the remainder of the time to work on homework stuff so that I can come in and troubleshoot to make sure that everybody understands where we are. All right? Cool beans.